Imagine standing in the middle of the world's largest power station. Thousands of megawatts are flowing through massive transmission lines. Turbines are spinning. Transformers are humming. Every second, an almost unimaginable amount of energy is being produced. Now imagine that no one needs that electricity. The factories are closed. The homes are asleep. The batteries are full. The transmission lines leading to distant cities have reached their limits. The electricity cannot be stored economically, cannot be transported efficiently, and cannot simply wait for tomorrow. In that moment, something extraordinary happens. The energy disappears, not because it was destroyed, but because it was never converted into useful work. For over a century, humanity has accepted this as one of the unavoidable limitations of electricity. Unlike oil, coal, or natural gas, electricity must be consumed almost exactly when it is generated. Every electrical grid on Earth performs an endless balancing act between production and consumption, every second of every day. But what if there existed a machine that could instantly absorb excess electricity anywhere on Earth and transform it into an asset recognized across the globe? That machine already exists. Its name is Bitcoin mining. Most people see Bitcoin mining as a process that consumes enormous amounts of electricity. Critics often point to the number of terawatt hours used each year and conclude that Bitcoin is simply wasting energy. Yet this criticism may be missing a much deeper question. What if Bitcoin is not merely consuming electricity? What if it is performing one of the most remarkable energy transformations ever invented? To understand this possibility, we must step away from economics for a moment and return to one of the most fundamental principles in physics. The first law of thermodynamics tells us that energy can neither be created nor destroyed. It only changes form. This law governs everything in the universe. Sunlight becomes chemical energy inside plants. Plants become food. Food becomes muscle movement. Muscle movement builds civilizations. Coal becomes steam. Steam becomes mechanical work. Mechanical work becomes electricity. Electricity becomes information. Information becomes economic productivity. At every stage of civilization, progress has never truly been about creating energy. It has always been about finding better ways to transform it. Seen through this lens, every human economy is ultimately an energy conversion system. Factories convert electricity into products. Computers convert electricity into calculations. Transportation converts chemical energy into movement. Even writing a book is, at its most fundamental level, the conversion of metabolic energy into organized information. Money itself is deeply connected to this process. Although we rarely think about it, money has always served as a way to preserve the value created by energy expenditure. When a farmer spends months cultivating crops, he is converting sunlight, water, soil, machinery, fuel, and human labor into food. When he sells those crops for money, he is really exchanging stored energy for another form of stored value. The same is true for every profession. An engineer converts years of education and mental effort into designs. A carpenter converts physical labor into furniture. A software developer converts electricity, computation, and knowledge into digital products. Money allows these different forms of energy transformation to become comparable. In many ways, civilization itself can be viewed as a giant accounting system for energy. Bitcoin introduces a fascinating new chapter to this story. Unlike traditional currencies, Bitcoin is not created by decree. It is not printed by a central bank. It is not issued according to political priorities. Instead, every newly mined Bitcoin originates from a measurable physical process. Electricity flows into specialized mining hardware. Inside those machines, billions of transistors switch on and off at astonishing speeds. Those electrical signals perform trillions of SHA-256 calculations every second. Almost all of that electrical energy eventually becomes heat. Occasionally, after an enormous amount of computation has been performed, one miner successfully discovers a valid block. That block becomes permanently embedded in Bitcoin's blockchain. New Bitcoin enters circulation. Notice something remarkable. Unlike fiat money, whose creation depends on institutional decisions, Bitcoin's creation depends on irreversible physical work. The blockchain does not ask who you are. It does not ask where you live. It does not care about your political beliefs. It recognizes only one thing: proof that a certain amount of computational work has actually occurred. This is why Bitcoin's proof of work system is so often misunderstood. People tend to focus on the computers, but the computers are merely tools. The true input is energy. The true output is economic scarcity. This relationship may appear simple, but it represents a profound innovation. For thousands of years, humanity has struggled with one central problem in economics. How do you create something that cannot easily be forged? Gold solved this problem because nature made it scarce. Finding gold requires exploration. Mining it requires machinery. Processing it requires enormous amounts of energy. No matter how wealthy someone becomes, they cannot simply decide to create mountains of new gold overnight. Its scarcity is protected by the physical cost of obtaining it. Economists sometimes describe this characteristic as unforgeable costliness. Bitcoin achieves something surprisingly similar, but through mathematics and thermodynamics rather than geology. No shortcut exists for mining Bitcoin honestly. No secret algorithm allows someone to skip the energy expenditure. No government can vote to eliminate the computational work required. Every valid Bitcoin block represents energy that was actually consumed somewhere in the physical world. In this sense, Bitcoin transforms electricity into verifiable scarcity. This is an extraordinary concept. Electricity itself is difficult to store. A surplus generated at noon by a solar farm may have little value if demand is low. Wind turbines operating at midnight may produce electricity that no one needs. Hydroelectric dams during rainy seasons often generate more power than nearby communities can consume. Traditionally, this excess electricity has been viewed as a problem. Sometimes generators are forced to reduce production. Sometimes renewable energy is simply curtailed. Sometimes electricity is sold at extremely low prices or even negative prices because there are no buyers. Bitcoin changes this equation. Instead of allowing surplus electricity to disappear unused, miners can purchase it and convert it into Bitcoin. In effect, they transform stranded energy into a globally tradable digital asset. This idea becomes even more intriguing when viewed through thermodynamics. Energy always seeks transformation. If no useful transformation exists, the opportunity is lost forever. Bitcoin mining creates a universal destination for energy that would otherwise have no productive use. A remote hydroelectric station deep in the mountains, a geothermal plant in Iceland, a wind farm in West Texas, a natural gas well where excess gas would otherwise be flared. Each of these locations may have one thing in common. They possess energy that is difficult to transport economically. Bitcoin does not require the electricity to travel. Instead, it allows value to travel. Rather than transmitting electrons across thousands of kilometers of expensive transmission infrastructure, Bitcoin mining converts those electrons into digital property that can be transferred anywhere on Earth within minutes. This is a subtle but revolutionary shift. Instead of asking, how do we move electricity to the customer? Bitcoin often asks, why not move the value instead? That distinction has enormous implications. It suggests that Bitcoin may not simply be another financial asset. It may represent an entirely new mechanism for monetizing energy itself. For perhaps the first time in history, electricity generated in an isolated location can become part of the global economy without first finding a traditional consumer. The energy is not literally stored inside Bitcoin. That would violate the laws of physics. Instead, Bitcoin stores the economic consequence of irreversible energy expenditure. The energy has already been transformed, the work has already been completed, the cost has already been paid. And because that cost cannot be reversed, the resulting Bitcoin carries with it a history of real-world physical effort. This perspective changes how we think about mining. Instead of viewing miners simply as electricity consumers, we can begin to see them as converters. They convert surplus energy into digital scarcity. They convert physical work into economic certainty. They convert local electricity into globally transferable value. That may sound like a small distinction, but history is often shaped by small distinctions. As humanity moves toward a future increasingly powered by intermittent renewable energy, one question becomes impossible to ignore. What happens when the world produces more electricity than it can immediately use? Perhaps the answer will not come from building ever larger batteries alone. Perhaps part of the answer already exists in warehouses filled with specialized computers quietly performing trillions of calculations every second. Because if Bitcoin can purchase electricity anywhere, at any time, and transform it into a universally recognized asset, then it is no longer merely participating in the global energy system. It may be quietly redefining how that system creates value. And that raises an even bigger question. If Bitcoin can become the buyer of last resort for electricity, could it eventually become one of the invisible forces shaping the design of tomorrow's global power grids? For more than a century, the greatest challenge facing electrical grids was producing enough power. Today, in many parts of the world, the challenge is becoming something entirely different. It is using all the power we can already produce. This may sound counterintuitive. After all, billions of people still lack reliable access to electricity, and global demand continues to rise. Yet in regions with rapidly expanding renewable energy, an unexpected problem has emerged. Sometimes there is simply too much electricity. When the sun shines brightly across thousands of square kilometers of solar farms, generation can exceed demand. When strong winds sweep across vast plains, wind turbines may produce more power than the grid can safely absorb. Hydroelectric dams experience similar moments during rainy seasons, when rivers deliver more energy than surrounding communities can consume. Electricity is unlike almost any other commodity. A barrel of oil can sit in storage for months. Natural gas can be compressed and transported. Coal can remain in stockpiles for years. Electricity has no such luxury. The moment it is generated, it must either be consumed, stored, or discarded. Although battery technology continues to improve, storing grid-scale electricity remains expensive and technically challenging. Large battery installations are valuable tools, but they are not yet capable of economically absorbing every surplus megawatt produced across entire nations. As a result, grid operators often face a difficult decision. They intentionally reduce electricity production. This process is known as curtailment. To many people, the word sounds harmless. In reality, it represents something extraordinary. Perfectly clean electricity is deliberately prevented from being generated because there is no immediate buyer. Imagine building an enormous solar farm capable of powering hundreds of thousands of homes, only to switch off part of it on a sunny afternoon because the grid has nowhere for that energy to go. This is not a rare event. As renewable energy continues to expand, curtailment is becoming increasingly common in many regions around the world. In other words, humanity is entering an era where the problem is no longer only producing clean energy. It is finding flexible ways to consume it. This is where Bitcoin mining begins to look less like an industrial process and more like an entirely new category of electrical infrastructure. Consider how most large electricity consumers operate. Steel mills cannot simply stop every 15 minutes. Chemical plants often require continuous production. Hospitals cannot disconnect from the grid whenever electricity prices rise. Data centers generally demand constant uptime. These facilities depend on stable, uninterrupted power. Bitcoin mining is fundamentally different. A mining operation can reduce its power consumption within minutes. It can shut down when electricity becomes scarce. It can restart when surplus electricity returns. Nothing about the Bitcoin network breaks when one mining facility temporarily disconnects. The global network automatically adjusts. This flexibility is almost unprecedented. From the perspective of a power grid, Bitcoin miners are not simply consumers. They are highly responsive loads. Instead of forcing the grid to adapt to them, they adapt themselves to the grid. This seemingly simple characteristic has profound implications. Every electrical grid must maintain an almost perfect balance between supply and demand. Even small imbalances can affect frequency and voltage stability. If generation exceeds consumption, frequency begins to rise. If consumption exceeds generation, frequency begins to fall. Maintaining this balance has always required expensive infrastructure, reserve generators, sophisticated forecasting, and constant intervention by grid operators. Now imagine millions of watts of electrical demand that willingly disappear whenever households, factories, or hospitals need more electricity. Instead of competing with essential consumers, Bitcoin miners can become the first to disconnect. When renewable generation increases again, they reconnect. Viewed through thermodynamics, this resembles a dynamic balancing mechanism. Energy that would otherwise be wasted is immediately converted into useful computational work. When that energy becomes valuable elsewhere, mining simply pauses. Nothing physical has to be transported, nothing has to be rebuilt. The electrical system continuously finds its most efficient equilibrium. Some researchers have described Bitcoin as an energy buyer of last resort. The phrase captures an important idea. In every market, the buyer of last resort purchases goods that nobody else currently wants. Bitcoin miners can perform exactly this function for electricity. If factories need the power, factories receive it. If homes require air conditioning during a heat wave, households take priority. If electric vehicles begin charging after work, miners can reduce consumption. But when no one else needs the electricity, Bitcoin mining creates demand where none previously existed. That demand changes the economics of power generation. Traditionally, investors hesitate to build energy infrastructure if they cannot guarantee enough customers. A remote hydroelectric project may produce abundant electricity, but without nearby industries or transmission lines, much of its potential remains trapped. Bitcoin changes that calculation. Mining facilities can operate directly beside the power source. They do not require densely populated cities. They do not require industrial clusters. They only require electricity and an internet connection. This allows power producers to generate revenue from energy that previously had little or no market value. In effect, Bitcoin can improve the financial viability of renewable energy projects located far from major population centers. Real-world examples are already beginning to demonstrate this possibility. In Texas, Bitcoin miners have participated in demand response programs, voluntarily reducing electricity consumption during periods of extreme grid stress. During heat waves, when millions of air conditioners increase demand simultaneously, miners can rapidly shut down operations, allowing electricity to flow toward homes and essential services instead. In Iceland, abundant geothermal and hydroelectric resources have long attracted energy-intensive industries. Bitcoin mining has become one of several industries capable of utilizing renewable electricity generated in locations with relatively small local populations. In Paraguay, enormous hydroelectric capacity has historically produced electricity that exceeded domestic demand. Mining companies have explored ways to convert portions of that surplus into economic activity rather than allowing its potential value to remain underutilized. Even natural gas fields offer another interesting example. Around the world, oil production frequently releases associated natural gas that cannot be economically transported. Instead of using it, operators often burn it in a process known as flaring. Flaring converts valuable chemical energy directly into heat and carbon dioxide without producing meaningful economic output. Some companies now deploy mobile Bitcoin mining systems directly at these remote sites. Rather than wasting the gas, generators convert it into electricity, which powers mining equipment. The result is not perfect, nor is it a complete environmental solution, but it demonstrates another important principle. Bitcoin can monetize energy that previously had little practical use. This idea leads to a much larger vision of the future. The 21st century will almost certainly consume far more electricity than the 20th. Artificial intelligence is expanding at an astonishing pace. Massive data centers require enormous computational power. Electric vehicles are replacing combustion engines. Industrial automation continues to accelerate. Desalination plants, hydrogen production, advanced manufacturing, and digital infrastructure all point toward one unmistakable conclusion. The future economy will be increasingly electrified. At first glance, Bitcoin appears to compete with these technologies for energy. But perhaps that is the wrong way to think about it. Competition assumes scarcity. Bitcoin's unique characteristic is that it thrives precisely where electricity is temporarily abundant and undervalued. Rather than permanently claiming energy, it can consume only what others do not currently need. In this sense, Bitcoin may function less like a competitor and more like a shock absorber. It smooths the economic volatility created by fluctuating electricity supply. It provides a predictable customer during periods of excess generation. It disappears when higher value demand emerges. This flexibility could become increasingly valuable as renewable energy continues to dominate electricity production. Solar panels do not negotiate with weather. Wind turbines do not ask whether electricity prices are high. Nature determines their output. Future power grids must therefore become far more adaptive than those built around coal and natural gas. Perhaps the most surprising aspect of Bitcoin is that its flexibility was never specifically designed for electrical engineering. It emerged naturally from the decentralized architecture of the network itself. Millions of independent mining machines respond to economic incentives without requiring centralized coordination. Each operator makes decisions based on electricity prices, mining profitability, and local conditions. Collectively, those individual decisions create a remarkably responsive global system. This raises an intriguing philosophical possibility. For most of human history, electrical grids have existed solely to serve human consumption: lights, factories, transportation, communication. But perhaps future grids will also serve autonomous digital economic systems. Machines may increasingly purchase electricity, convert it into computation, and exchange the resulting value across global networks without direct human intervention. If that sounds futuristic, remember that Bitcoin has already been doing exactly this for more than a decade. None of this means Bitcoin is a perfect solution. It does not eliminate the need for batteries. It does not replace transmission lines. It does not solve every challenge facing renewable energy. Nor does it guarantee that every mining operation uses clean electricity. Those are important questions that deserve honest debate. Yet reducing Bitcoin to a simple measure of annual electricity consumption risks overlooking a far more profound development. Its greatest innovation may not be financial. It may not even be technological. It may be thermodynamic. Bitcoin is the first globally distributed economic network capable of transforming location-dependent, time-sensitive electricity into a universally transferable digital asset on demand. That capability has never existed before. Whether history ultimately remembers Bitcoin as digital gold, programmable money, or something entirely different remains uncertain. But one possibility deserves far more attention than it currently receives. Perhaps the real debate was never about how much electricity Bitcoin consumes. Perhaps the more important question is this: in a world where energy is becoming cleaner, cheaper, and increasingly difficult to distribute efficiently, could Bitcoin become the bridge between the immutable laws of physics and the evolving architecture of the global financial system? If the answer is even partially yes, then Bitcoin is not merely participating in the future of energy. It may be helping to shape it.